We have spent several weeks discussing how to design data warehouses, the importance of collecting and analyzing data, and the challenges faced in creating these types of systems. There's one more piece I want to cover that is specific to data warehousing, and that is how we manage or administer these warehouses after they are up and running. As you can probably imagine, just like any other system, there are many different tasks involved in keeping this type of system running efficiently. If you have ever administered a large database, you know how much work goes into keeping the data in a consistent state, monitoring system resources to ensure users have access when they need it, and there is the constant need to find ways to make the information flow more efficiently. The work required in a data warehouse is similar since it is a giant database, but since they are used for a different purpose than traditional databases, there are some other tasks unique to their operation. Managing a warehouse requires managing the resources of the systems, the functionality of the system, how the data is processed, and how the queries and algorithms are used to keep everything running efficiently. Load balancing is a key area that needs to be managed in a data warehouse architecture. Load balancing is a way to balance the load of operations across several different systems so that one single system does not become overworked or overloaded. This is a concept used in many different areas of computer science that allows the processing of large amounts of data or communication streams to be split up into smaller pieces and then sent off to another system for processing before everything is recombined. It's common for a large data warehouse to have rooms or even entire buildings full of computers designed exactly for this purpose. Even one really powerful server is limited by hardware resources and has a finite amount of CPU and RAM capabilities, so combining the resources of hundreds of powerful systems together can balance out the workload without ever overloading one system. It is a simple concept that is actually quite sophisticated in its implementation. The software running on each system is able to communicate across the network to the other systems, and these systems are able to seamlessly process requests with parallel operations and send the results back to the user. Without load balancing, we could end up with a lot of bottlenecks in our operation. A bottleneck is a term we use to describe when one thing causes all operations to become congested and slow down. If you have ever been on a busy road during a lane closure, you have experienced a bottleneck. Trying to push the same number of cars through 2 lanes instead of 3 causes a lot of congestion in the traffic and a lot of frustration with the drivers. Imagine the same concept in processing data. The time required to process 1 million requests on one computer can be cut in half simply by adding a second system. Adding 2 more systems can cut this in half again, and as we continue to add systems to the architecture, we will continue to lessen the amount of time needed to process any given task. The same query that may have taken half a day to complete on one system could be finished in just a few minutes when load balancing is used because the bottlenecking is reduced. Load balancing can also be scaled to add more systems as the needs of the data warehouse grow. So it is wise to start at the level needed and then manage the growth over time. Because we have load balancing to manage bottlenecks in processing, we also need to manage the queues where all the query requests are waiting to be processed. You should have heard of a queue in other courses. It is essentially a line where different processes are waiting to be run. In our case, it is a line of queries waiting to be run against the data warehouse. If your warehouse only had one user conducting queries, this would be easy to manage. But we have to consider the possibility that there will be several users and each one is competing for their queries to get processed as quickly as possible. Generally speaking, this is managed in a first in, first out order by allowing the queries to be processed in the same order they were submitted. But occasionally, we may need to bump something to the top of the queue because it has a higher priority, or we may need to pull something out of the queue because its construct is causing the system to take too long to respond. Even with load balancing, a poorly constructed query can create a strain on resources. Managing these queues are another way we maintain efficient operations and keep the users from waiting too long for their results. Complex analytical queries are at the heart of operations within a data warehouse. Imagine running a query that has to search through a billion rows of data looking for the names of all men between ages 25 and 35. It would take a significant amount of time to return this result. Well, what if we narrowed it down by adding another requirement that these men need to live in a specific city? Now the system would have to look for three pieces of data in every row: the gender of the person, the age of a person, and the city that they currently live in. This is actually a pretty simple query compared to the types of queries run against a data warehouse. But you should be starting to formulate the idea that searching within a lot of data for specific pieces of information can take a significant amount of time and system resources to complete the operation. And the more data that needs to be searched through, the longer it can take. We also have to consider that the data in these warehouses rarely sits on one computer or on one hard drive. Oftentimes it is split across different systems, so we also have to deal with queries that cross onto these other systems. But our queries are not limited only to searching for information. We discussed in an earlier lecture that these warehouses usually have multiple sources from where they draw their data, and it is very easy to assume that in one of these situations you will end up with redundant data that will need to be removed. So we also have to craft algorithms that will search for the redundant data and remove it from the warehouse. This redundancy issue is incredibly important because it can completely skew the results of queries. When the United States conducts a census, they are looking for exact numbers of populations in different areas of the country, as well as the demographic of those areas. One major use of a census results is to determine funding for a variety of programs, and if there is a lot of redundant data, some sections of the nation could get a lot more funding in their programs while others get much less. Of course, the census data is used for many other things, but this is one example of where redundancy can skew the information enough to change how it is used. We need to have good algorithms that can search through the data to eliminate the redundancies without deleting anything else. All databases have a problem with fragmentation. As data is added or modified, fragmentation can occur, which causes performance to slow down and storage space usage to increase. Fragmentation can occur in one of two ways. First, file fragmentation causes the data to be out of order on the physical storage. When this occurs, the system has to look on different sections of the hard drive to pull all the information into memory as it is being processed. Moving back and forth on different hard drives consumes a significant amount of time and will slow down these operations. Page fragmentation is the other possibility, and this occurs when pages are split to make space for more information, often leaving blank space on the page. This causes more storage space to be used and can eat away at available space if it is not dealt with. Once again, we have a need for algorithms to work through the data warehouse environment and defragment any files or pages that we can maintain an efficient operation. If you have ever used the same computer for several years, you have probably noticed that it starts to slow down over time. Fragmentation is one of the causes of this problem. But personal computers are also much smaller than a data warehouse, so imagine this fragmentation on a much larger level. The level of effect on these systems can significantly hamper operations. So you can see that there are some very important tasks to manage when running a data warehouse. It would be nice to spend a lot of time designing and building it so that it never needs any other oversight or management, but that is not the case. These systems do a lot of work and need to be managed appropriately, or else they will eventually start to break down. It's not much different from maintaining a car. We need to change the oil, air up the tires, fill up with gas, and manage some other preventative maintenance tasks if we want our cars to continue to run smoothly. Many cars can continue to operate for several hundreds of thousands of miles with the right maintenance. It is the same concept with data warehouses. Managing them efficiently will keep them in operation for a long time and will keep the queries churning out the vital information we need to make decisions, conduct research, or to fulfill whatever task they are used to accomplish. Some of these management tasks are a full-time job all by themselves, like creating algorithms to eliminate redundancy or fragmentation, and others can be monitored continuously in the background, like load balancing. But each of the management processes discussed this week are vital in keeping a data warehouse operation at peak potential.